So today we're going to learn about Michael Faraday and Henrik Lenz and how they added on to what we know so far about how magnets and current interact with each other, or conductors, current carrying conductors and magnets interact with each other. So let's start off with Michael Faraday. He discovered that when a permanent magnet was moved in and out of a coil of wire, a current was introduced in the coil. So moving a magnet in and out, a current was introduced. So here's a little example I have to help show this. So here, I have a magnet, I have coiled wire, and a voltmeter. Now, if I move this magnet in and out, look what happens to the volts. I end up getting volts. Now, if I have a potential difference, that must mean there's current being applied here. So I move it one way and the other, it changes direction, the current. So it depends on which way I'm moving the magnet to, which way the volt's going, or the current will be going. So another thing here is, if I move slowly, there isn't much current. If I move fast, there's quite a bit of current. So that is generally Faraday's idea. So he said, by moving a magnet, or if I move something to cut magnetic fields, because if we think about this, magnet has magnetic fields, I'm going to create a current if I move a conductor through magnetic field. So what does that mean? Let's take a look at this here. Essentially, this was his idea. So here we have two magnets, right? We have a north and a south. Well, the magnetic field's going to go this way. And in my first one, I am looking at positive charge. And we already know this, so if we're looking at positive current, we are looking at my right-hand rule. And we already know that velocity, magnetic field, and forces are all going to be perpendicular to each other. So here we're looking at how the force is applied to my charges. So I'm going to use my right hand here, and I'm going to follow my velocity, my magnetic field, and the force up will be my proton movement. So once again, velocity, magnetic field, force up, or you could look at it this way, is going to be my movement. So that's the right-hand rule. And as we move this through, notice the velocity is important here. So here's kind of the voltage, how we can figure out the voltage. It's velocity multiplied by magnetic field multiplied by the length of my the amount of wire being cutting through the magnetic field. So if I increase the velocity like we looked at before, I'm going to increase my voltage. I'm going to increase the amount of protons, in this case, moving up. Now this one here, we're looking at negative with electrons. So in that case, we have to use my left-hand rule. So once again, my magnetic field, velocity, force going down. The force is pushing the electrons down, which makes my current, in this case, coming down. All right? So essentially what he's saying is, by moving the rod in a magnetic field, we can motivate the charge, electrons or protons, to move in the wire, thus creating a current or voltage. So, what does that mean? We have to think about this here. If current makes magnets, could magnets make current? Well, that's pretty much what we just came up with. So current, we know before, makes magnets, and we know magnets make current. So we've discovered now here a way of making current, which becomes very important later on. So here I have a song for us to listen to help us understand what's happening.
Together let's build a new nation that's founded on truth and on love. No war, no disease, no privation, a senator's blessed from above. But what in this country so gleaming shall our guiding principle be? Oh, What song from our lips shall be streaming as we march so victoriously? Why, Faraday's law of induction, the law of all sea and all land. No lies, no deceit, no corruption, in this law so complete and so grand. Our children will sing it in chorus, circulation of vector cap E. Yes, they'll sing as they march on before us, equals negative d by dt. Oh, magnetic flux through a surface, they'll conclude as we strike up the band. We'll mark all our points with our purpose, on Maxwell's equations we stand. It's Faraday's law of induction that allows us to generate power. It gives voltage increase or reduction. We could sing on and on for an hour about Faraday's law of induction, the law of all sea and all land. No lies, no deceit, no corruption, in this law so complete and so grand.
So basically what we discovered here is Faraday pretty much came up with how to induce current. Okay? Now the first people to really use this on a big scale was NASA. And they looked at the idea and said, hey, look at this. Earth is a gigantic magnet. If we send a big tin thing around Earth, or big conductor around Earth, won't it technically be cutting the magnetic fields? And if it's cutting magnetic fields, we are making a current. So that is how we could pretty much create electricity on our spaceship, or on the International Space Station. It just cuts around Earth's magnetic fields, creating electricity. Now there are other applications on this that are very important. For instance, wings on an airplane must have grounding material. Because if we think about this, airplanes, a lot of times they're flying around Earth, and they're flying pretty fast, and they'll be cutting magnetical fields. Now if they're cutting magnetical fields and magnetical lines, what's going to end up happening is they're going to create a current. And what happens is that current can interfere with the current or the electrical equipment in the jet. So, now, some interesting notes about this induced current. We know one, magnets make current, but current in turn makes magnets. Now here comes someone called Frederick Emil Lenz. Okay, so Lenz had an interesting experiment that you will see here.
Some physics, using a little metal cylinder and plastic ends, and a copper tube down which it drops at high speed, as you would expect. You can see it through the window. However, if we take another metal piece, exactly the same as the first, but highly magnetize it, watch what happens. It descends so slowly, there's nothing to inhibit it, apparently, and yet it descends so slowly. Why? This is Lenz's law. This descending magnet is creating a transient current in the copper tube, and that itself creates an opposing magnetic field that tries to stop it getting past.
So now this is very interesting what happens here. So this video that I got off YouTube shows two tubes. First he drops a non-magnetized piece of metal down a tube, and it lands like you expect. Then we have a magnetized piece of metal drop down a metal tube. They're the same weight, but it takes a lot longer. Now this is interesting. So we know from before that magnets make current, current in turn makes magnets. Now we think about this. It could work both ways. If we're making magnets, we could either speed up the process and accelerate the magnet down, or it will slow it down. But in this case, it slows it down, and here's why. So, basically what Lenz came up with is induced current will generate a magnetic field, and it is possible to predict the direction of the magnetic field using our left hand. So we're going by induced current here, which Faraday found out, and now Lenz added to it, which is kind of interesting here. So right here we have a north side of the magnet. So my magnetic field is going to look like this. It's going to be coming out. Okay? Now, we want to know which way the current will be going here. Well, now if we think about it, if this is south, what's going to happen is it's going to attract this, and this is going to speed up. We saw in that little demonstration from YouTube that it doesn't speed up at all. It slows down. Now, why would it want to slow down? Well, if I think about it, this is forcing the electrons to move. The electrons don't really want to move. They want to stay still. So they're going to move in the opposite direction to prevent itself from creating a magnetic field and slowing down this magnetic field. So that's why they'll move in the opposite direction. And you might want to think of this because of the conservation of energy. We can't, if they went in the one direction to create a magnetic field that will allow this to speed up, well, then our electrons are going to go faster and faster and faster. We're going to be creating more and more energy, which doesn't quite make sense. They're going to want to resist the flow. So for this, we're going to have to use my left-hand rule because we're thinking of electrons. And I want my magnetic field to go this way, right? Coming out. So I'm looking at that. We're going to go magnetic field this way, and that means my electrons are going to be flowing this way around the coil. That's going to be the way my electrons flow. Now, if I'm using the south one, that means this now has to be south. So it has to be the exact opposite. So if I'm using the south pole, I'm going to reverse my hand this way. So then now I know my flow of electrons is going this way. So before, my flow of electrons is going that way. Now my flow of electrons is reversed for the south, so it repels it. Now, this creates many interesting things. Okay? And it also makes us think about motors. When we get to motors then, technically we are creating a magnetic field, and they're going to be repelling each other, and that comes into other questions that we get to later. So now with all of this ideas done, we know that by moving magnets inside and outside, or in and out of a coiled wire, we could create current. So with this, I come up with my own solution on helping with global warming and reducing fossil fuels, and also maybe helping us prevent more dams being built up. We could just give a whole bunch of monkeys speed. We'll be forced to plant more forests to feed them bananas, and they'll just constantly throw magnets in and out of coiled wires, enjoying themselves and going forever. And then we'll be clear of everything. The only problem maybe is animal activists may not be too happy with that idea. But other than that, it might be an easy way to create